Everything's been solved. Everything has been solved. And this is like more the conclusion of like what's going on.
Nice title slide.
Yeah.
This is not up to some
No. I can give you some names of some people that will be able to handle that.
So nothing saying the broadcast.
You just always hear like nice talk. It's because you always talk.
All right, so I guess we will continue now. Before we start with the next talk, I would like to ask if there's anyone that would like to present an open problem in the open problem session after the talk, because so far we have none.
I can volunteer to get beers. Make sure that someone presents an open problem.
All right, maybe just think about it in the course of the talk, and if you have an open problem, we can start the session after the talk. So the next talk will be by Raghu Meka, and he's going to talk about lifting non-negative ranks.
Hello everybody, I'll talk about lifting non-negative rank. This kind of is very connected to the talk that you saw before by Meka, and this is based on joint work with Pravesh Kothari and Prasad Raghavendra. So I'll start by stating the main theorem informally, and then we'll state the crux of the theorem more formally. So the main theorem is that for many CSPs that we all care about, if you want to beat the trivial algorithm where you just don't even look at the instance, make a random guess, and check how well it does, to beat this trivial algorithm by an LP, you need sub-exponential size LPs. So for example, for 3-SAT, for max 3-SAT, there's a trivial 7/8 approximation algorithm. Just take a random assignment, it satisfies 7/8 fraction of the assignments and of the constraints. If you want to get slightly better, 7 or 8 plus 0.01, then you need a linear program whose size is exponential, or exponential in n to some constant. Okay. And the same holds for max cut. There's a trivial algorithm for max cut, which is take a random cut that cuts half the edges. If you want to do 0.51, then you need a sub-exponential size LP. Okay? And the previous best result in this line was due to Chan, Lee, Raghavendra, and Stoyer, who showed that to beat the trivial algorithm, you needed quasi-polynomial size LPs. And what we do here is to get it all the way up to sub-exponential. And it's more than this. I mean, the way I presented it, it sounds like a negative result in that we're saying that LPs cannot solve some problems. But it's, the main result is an upper bound or an algorithm which says that for CSPs, as far as CSPs are concerned, sub-exponential size LPs are as powerful as a special kind of LP. Okay? Are as powerful as Shirley-Adams relaxations of roughly the same size. So if you start with size 2 to the s, you end up with something which is like s rounds or poly s rounds of Shirley-Adams. Okay? And once you have this, using known results, known lower bounds for Shirley-Adams, you get the results that I stated before. So I'm not going to talk about either of these two theorems today. I just stated them because those are the main motivation for the work in the first place. But how do we talk about LPs for CSPs? So I said these are lower bounds on the size of linear programs. I want to characterize how you can solve a CSP by arbitrary linear programs. And there's a way to formalize this using the language of extended formulations. We see many talks in this workshop on it, but they were all for polytopes. But now we're talking about approximation problems, so you need to extend those definitions a little bit. But at the end of the day, all of these definitions reduce by this very nice result of Yannakakis, kind of further expanded on by Chanley, Raghu, and Stoyer, to computing the non-negative rank of certain matrices. Okay? So that's going to be our starting point. You can get all of these size lower bounds for CSPs and the simulation results if you can understand the non-negative rank of certain matrices. All right, I'll tell you what these matrices are by giving an example, and then we'll talk about what sorts of things we'd like to know. Let's look at an example, which is max cut. So let's say I want a C, S approximation for max cut. This is something that we saw in Madhur's talk, for instance. So here I want my algorithm to output a value which is at most C. If I tell you that the optimal cut is at most S. Okay, S is like soundness, C is like correctness, and so on. And what's the best size LP for this problem? The best you can do can be characterized by the following matrix, which I'll call M cut. So the matrix, the rows are indexed by graphs whose best cut value is at most S. The columns are indexed by cuts, which are S. And G, Sth entry is basically C minus cut G of S. Okay? And just from the definition, you can see that this is always non-negative. And following the work of Yannakakis, CLRS showed that the best size LP achieving the least size LP to solve this problem for max cut is equivalent to the non-negative rank of this matrix. Okay? So we started out looking for all possible LPs which can do some things, and we ended up with a very concrete question, which is to understand the non-negative rank of this matrix. Okay? So how do we approach the non-negative rank of this matrix? First of all, let's just, we saw this definition already in Meka's talk, but let me introduce the definition again. So let's say I have a non-negative matrix M. Then the non-negative rank of matrix is the min over all R, such that I can write M as a sum of rank 1 matrices, of R rank 1 matrices, where each matrix, the factors are non-negative. Okay. The usual notion of rank, except that you also impose the non-negative constraints on the vectors that are involved in the factorization. And this is very well connected. I mean, this is sort of the core tool that's used in studying extended formulations. And proving lower bounds for non-negative rank is not easy. In fact, the first exponential separation was only proved maybe about 5-6 years ago due to Fiorini and others. Okay. So what this work does is actually give a technique for lower bounding the non-negative rank of a family of matrices, of a class of matrices. And what is this class of matrices? Those are pattern matrices. Okay? So here's the outline of the talk. I'll first talk about pattern matrices and how we can bound the non-negative rank of pattern matrices. And we'll see how to do this using certain tools from communication complexity. So if you want to take one thing away from this talk, I'd like it to be this second part, which I think is the more conceptual part of this work. And then if there's time, I'll briefly sketch the decomposition theorem. Okay? So let's start with non-negative rank of pattern matrices. So pattern matrices are special kinds of matrices which you build out of functions. So I start with a function on the hypercube, which takes n bits and outputs a real number. And from this, I'm going to build a matrix. And pattern matrices are the things that Meka called lifted functions. Okay? So the matrix, the columns are going to be indexed by x, and the rows are going to be indexed by y. Think of x being Alice's input and y as being Bob or column player's input. And the inputs come from, the inputs are n symbols. They're the symbols over some alphabet sigma. Okay. We now combine these inputs to get an input for our function f. So we need a gadget g, which takes 2 symbols and outputs a Boolean value, a 0, 1 value. And we now define a function mf of x comma y, where the first input to our function f is obtained by applying the gadget to the first 2 symbols of Alice and Bob. Okay? And the second input is going to be the output of the gadget g, the function g, on this second symbols of Alice and Bob, and so on and so forth. So we'll call this function f the outer function. This function g is called the gadget. Okay? You should think of the gadget as being something small, the outer function as something being more complicated. Okay? And this gives me my function mf, which is f composed with g to the n. Pictorially, we have the matrix which looks like this. As I said, the rows are indexed by symbols of length n over the alphabet sigma, columns similarly, and the xyth entry is the output of f of g to the n of x comma y. Okay? So these are called pattern matrices because in some sense, the pattern of f is embedded in this matrix in many, many places. You'll see a copy of f in every row, every column, and many other places. Okay? And what we'd like to, the main meta question when you look at these matrices is to understand various measures of these matrices, of the matrix, the lifted matrix MF, in terms of some property of F. Okay? So if I want some notion of rank of, I want to characterize some notion of rank of the matrix MF in terms of some corresponding measure of the outer function little f. For example, it's fairly easy to see that the usual notion of rank, if I look at the rank of this matrix MF, it's exactly characterized by the degree as a polynomial of my outer function f. Okay? But for this work and for the application that we're interested in, we need to understand the non-negative rank of this lifted matrix MF, of the pattern matrix MF. So here's the setup again. We have our outer function f, which takes non-negative values. We have our gadget g, which combines two symbols and produces a bit. And from that, we can define our lifted function, lifted matrix. And I'd like to know whether, I would like to characterize the non-negative rank in terms of some measure of f. So what measure of f should you use? It's a pretty natural measure given the context. If you play with it, then you'll end up with this measure. So what's the measure? It's a non-negative analog of degree. Well, almost, but there's some subtlety here. So it's called degree plus. So degree plus of f is the least number d, such that I can write f as a sum of non-negative Juntas. Okay? I'm going to write f, which is a non-negative function, as a sum of non-negative functions, but I want each of these small functions involved in the summation to only depend on d variables. Okay? So each of these HIs only depends on d variables. The least d for which we can do that is degree plus. And it's easy to see that you get an upper bound on the non-negative rank in terms of degree plus. Okay? So the non-negative rank of the lifted matrix is at most exponential in something which depends on the alphabet size, that's not too important, times the degree plus of f. Okay? Essentially, you can just expand each of these HIs to get a corresponding nice rank 1 term. Okay? So given this upper bound, the main question we'd like to address is whether there's a corresponding lower bound. Is this bound tight or is it not? Okay. So we're going to show that it is basically tight, but for a specific choice of the gadget and alphabet. So the gadget we'll look at today is the one that Meka also mentioned, which is the inner product gadget. So think of the alphabet as being strings of length b, where b is going to be some parameter. And the output of the gadget is the inner product mod 2 of these two b-bit strings. Okay? It will also work for more general gadgets, but inner product is the most natural one for which this analysis works. So our real main theorem, from which the results I mentioned on the first slide follow, is that as long as b is at least some constant times log n, I'm ignoring constant factors, and I'm going to normalize so that the expectation of my function is f. This is just a normalization term. Then the non-negative rank of my lifted matrix is at least exponential in b, which is log of the alphabet size, times degree plus of f with a small additive shift. Okay? So if you compare this to the upper bound I mentioned on the previous slide, this is tight except for the omega 1 in the exponent and this additive shift of 100 over n. Okay. This additive shift doesn't matter for our application, so it's fine for things that we do. Okay. Any questions?
Where was degree plus before in the upper bound?
It's in the exponent again. Yeah.
The parameter is
It's in the exponent. Yeah.
It's in the exponent. Exponential b times degree plus of f. So the lower bound is basically b times degree plus of f in the exponent, except is f plus 1 over n. Okay.
This is for every G.
No, this is for the inner product. This is for the inner product gadget.
The lower bound is, but the upper bound is for every G.
The lower bound is for inner product. The upper bound is for every g. Okay. And I mean, if you make your g trivial, then your lower bound will break. Okay. So once you have this, I should say something. Right. So what was known, I mean, these lifting theorems for non-negative rank were also looked at before, something that Meka also mentioned. There is some work in, there is a lifting theorem which works up to some range in CLRS. And in this work with Meka, Gios, Shahar Lovet, Thomas Watson, and David Zuckerman, we showed a lifting theorem for approximate non-negative rank. Okay? It's a similar characterization, similar lower bound on the approximate non-negative rank of matrix in terms of the approximate degree of the function. Okay? So you start with something weaker and also end up with something slightly weaker.
So,
yeah.
So here the difference is the approximation is very controlled, like you're just adding.
But you're just adding, yeah. Yeah. So once we have this lifting theorem, you can just plug this into the abstraction in CLRS to get the CSP results that I mentioned. Okay. And one reason is that if you think of this M-cut matrix I mentioned before, I wrote down, these pattern matrices can be found as sub-matrices of this cut matrix that I said. So that's how you get the lower bound.
And just to be, so F will be like, as in previous work, just like a hard instance for
F is going to be just some counting problem, like a hard instance for Shell atoms. Yeah. Okay. And another thing to keep in mind is that to get the CSP results, for example, you cannot use just a lifting result for approximate non-negative rank. The matrices that show up when you're trying to show lower bounds for CSPs, they have small approximate non-negative rank, but big non-negative rank. So any technique which kind of is trying to lower bound only the approximate non-negative rank is not going to work.
So why do they have small approximate?
You can just, you can get like an n log, basically like log n times log 1 or epsilon base by sampling. When you, if you're exactly, if it's additive of epsilon, you can just get, can get by with log 1 or epsilon bits of communication. Okay. So here's the outline. Again, I stated the main result, which is a lifting theorem for pattern matrices, which gives a lower bound on the non-negative rank of pattern matrices. And now let me tell you how the main, what's the crux of the proof. So the crux of the proof is something that comes out of communication complexity. We call decomposing high min-entropy product distribution. So let's get there a little slowly. So let's recall our setup. We have this outer function f, we have our gadget g, we have our lifted matrix, and we'd like to show a lower bound on the non-negative rank of the lifted matrix. Okay? Let's work by contradiction. So every lower bound is real and upper bound. In that sense, what we'll say is that if the non-negative rank of this matrix is small, then we'll show that function f has small degree plus. Okay? Okay, so starting from this assumption, we would like to show or say that degree plus of f is small, and that will give us a contradiction that we want. So how can we find a small degree plus certificate for f? Let's see what the non-negative rank assumption means. So just from definition, MF having small non-negative rank means that I can write it as sum of rank 1 matrices where the factors are non-negative. And since these are non-negative, I'm going to normalize them so that these factors actually correspond to distributions on the rows and columns. By just changing the scaling term, can make sure that I can write MF as lambda I, which is kind of the scaling term, times UI, which is now a distribution on the rows, times VI transpose, which is now a distribution on the columns. Okay? And our equality, or the definition of the lifted matrix, says that f of g to the n of x comma y equals this for all x comma y. And as I said, we call them pattern matrices because you can find many copies of f embedded in this matrix, right? And we're going to exploit that in a strong way, but also sort of in a weak way when you think about it analytically. Since this equality holds for all x comma y, it will hold when I average over some sets of x comma y. Okay? But I'm going to average over a specific set of x comma y. So let's fix this n-bit string z, which is just a Boolean n-bit string. And I'm going to sample x comma y, whose image under the gadget g to the n is actually z. Okay? So look at all pairs of rows and columns whose output under the gadget is z. Okay? And let's look at f of z. Since the output of the gadget on every one of these points is exactly z, the expected entry of the matrix under this distribution is also f of z. Okay? And by linearity of expectation and using the factorization representation I had before, I can move the expectation inside. Okay? All of this is very straightforward, but we'll end up with something looking very nice in a minute. And so we are looking at summation lambda I, expectation of ui of x and vi of y, where x comma y are being sampled from this joint distribution. Okay? And there's a simple way to kind of switch variables and make this distribution independent. Okay? Instead of sampling from x comma y so that the gadget output is z, I can sample x comma y independently and look at the expectation of g to the n of x comma y equaling z. Okay? So by changing another scaling term here, everything boils down to looking at the expectation of sampling x under the distribution ui and sampling y independently from a distribution vi, and looking at the probability that the output of the gadget equals this string z. Okay? So we have this quantity here, and what can we say about these functions? That's the main question we'd like to understand now. Because let's say we were very lucky and we maybe just had like a few of these components, then can we say something nice about these functions on the hypercube that we get? So for example, it would be very nice, and we can all go home, if these functions were all just sum of non-negative Juntas. Yeah?
What are UI and VI? Oh, now you're thinking of them as measures, right?
Yeah. UI and VIs were distributions, right? Yeah.
Sorry.
Okay, so basically we're doing this experiment where I sample x independently, and x according to UI, and y independently according to VI, and then I'm checking whether or not the output of the gadget equals my input string z. Okay? And if these functions are simple, then I'm done. For example, this is a D junta, then I get a nice representation, everything is there, we are done. We had a small degree plus representation. Okay? So let's abstract this out even further, and let's look at the following quantity. I have two distributions on sigma to the n, on the rows and columns. I sample a row index independently according to one of them, and a column index independently according to the other one. And I look at the probability that the output of the gadget equals my input string z. Let me call that AUVZ for acceptance probability of z under the distribution u comma v. Okay? So can we identify any structure in AUV? If these functions are simple, if they were small degree Juntas, for example, then we would be done. Unfortunately, that's not true. That cannot be true all the time, because without any restriction, u and v could just pick out one particular point in the matrix, right? It could just be a delta function. And here's where the small non-negative rank shows up. The thumb rule to keep in mind here is that small non-negative rank corresponds to the factors being high min-entropy distributions. Okay? And here, by min-entropy, we say distribution has min-entropy at least k if every event under the distribution has probability at most 2 to the minus k of occurring. Okay? So no event is more likely than 2 to the minus k. So if you have small number of factors, then you can sort of prune out some factors to ensure that all the remaining ones have high min-entropy. And now let's ask the same question again. So we have our alphabet sigma, which is 0, 1 to the b. We have our gadget, which was the inner product. Let's look at the alphabet size being slightly bigger than log n. And now we have two distributions u comma v. Both of them have very high min-entropy. How high? They're basically missing entropy corresponding to t blocks or t symbols. Okay, so the entropy is at least n minus t times b. What can we say about AUV? Well, let's look at some examples. The simplest example I can think of high min-entropy distributions are uniform ones. Right? So u and v are just uniform on sigma to the n. What is AUV in this case? Well, g is a balanced function, so it's just going to be uniform as well. Okay? So g to the n of x being uniform and y being uniform is a uniform distribution. So the probability that it equals something is actually a constant. Okay? It's exactly going to be 1 over 2 to the n. That's it. What other sort of the next complicated case I can think of for distributions which miss t symbols of entropy is to force it to miss t symbols of entropy. So let's say I fix the first t symbols of u, first t symbols of v, and everything else is uniform. Okay? So the blue parts are fixed strings, everything else is uniform. Then if you look at the output of the gadget, what you'll get is the first t symbols are fixed and the rest are uniform again. Okay? So in this case, the acceptance function is actually a t junta. It's a t non-negative junta, in fact. Okay? This looks good, but there's one more slightly bad case, which is I still have t fixed coordinates, but the others are not perfectly uniform. All right? So the first t are fixed in both u and v. And in the remaining, in u, the distribution is product on the coordinates, but each coordinate just has very high min-entropy. It's not uniform, but has min-entropy, let's say, almost the full b, which is 0.9 b. Okay? What can you tell me about the acceptance function then? Well, it turns out that even in this case, the first t coordinates are fixed, so those things are lost anyway. The remaining ones, you still get uniform distribution. Okay? So the output is again a t junta, and here's where we use the property of the inner product gadget, that it's a two-source extractor, meaning if I give you two symbols with very high entropy, then the output is almost close to being uniform. Okay? And the sort of main structural result is that these three cases essentially cover all possible cases. Okay? So concretely, to formalize this, we need the notion of blockwise density, which was introduced in work that I mentioned before. So let's have a distribution x, which is sampled from u, which has n symbols. We'll say it is blockwise dense if the following holds. If I look at any subset of coordinates, the min-entropy there is nearly the maximum possible. So the min-entropy rate, there is a constant. So in particular, the min-entropy of x restricted to I is at least 0.9 times the maximum possible, which is b times I. So whenever this is satisfied, we call x blockwise dense. Okay? And then there is conjunctive blockwise dense, which kind of generalizes the second case that I mentioned before, which is basically blockwise dense with few fixed coordinates thrown in. Okay? So here I have d coordinates which are fixed. The rest are all blockwise dense. Okay? And then there is aligned blockwise dense. So here I have two distributions which are blockwise dense and some fixed coordinates, but I also want the fixed coordinates to align. Okay? So I have u comma v. They have some d coordinates which are fixed in both of them, and in everything else they are almost uniform in the sense of being blockwise dense. Okay? And the decomposition theorem says that if you have any two high entropy distributions, u comma v, you can write them as a convex combination of aligned conjunctive blockwise dense sources with exponentially small error. Okay, so let me elaborate on the parameters. So here are u and v, which are high min entropy. So they're missing t symbols of entropy, right? I can write them as a convex combination of dCBD sources, which are aligned. So each one of them has roughly some constant times t many fixed coordinates. In the remaining, you have blockwise dense. Okay. Up to some exponential error in the t, the number of coordinates that you're fixing. Okay. This is the main decomposition theorem. And it turns out that once you have this, you can show what we really wanted, which is that if you start out with these functions, distributions u comma v, being very high min entropy, then the acceptance function is a non-negative sum of O of t non-negative Juntas. Okay? And this we can plug into where we came from and complete the analysis. So in the remaining couple of minutes, let me say a couple of words about how to prove the decomposition theorem. I won't say much about the analysis, but the proof, at least how we find the decomposition, is fairly greedy. You do the thing that is most natural in some sense. So what's our goal? We have this distributions x comma y, or random variables x comma y sampled from u comma v, which have very high min entropy. Okay? And we'd like to decompose them into this nice structured sources. Well, if they were already structured, we are done. Okay, we can go home. But if not, then there must be something which is violating the constraint. So for example, let's say x was not blockwise dense. That means it has smaller entropy than it should have in some subset of coordinates. Let's call it I. So there is some subset of coordinates I where it was giving too much mass to one specific assignment than it should have. Let's call it alpha I. So we have this kind of violation of our blockwise density condition. And to fix it, what we do is just condition on it. Okay? We split this source x comma y into two pieces. One where we condition on this event happening, the event that's violating the blockwise density, and the other one which is a negation of it. Okay? The hope is that by conditioning on it, we at least get blockwise density in the remaining. Okay? Well, this is good, but not quite good, because here x and y are no longer aligned. We fix some coordinates in x, but not in y. So how do we fix that? I'm going to be really sort of greedy again and consider all possible conditionings of y in the things that I fixed in x. Okay. I just can look at all possible conditionings of yi, so I get 2 to the b times I many branches. All right, and then I iterate. Okay, are each of these pieces blockwise dense? Yes, maybe no. I split again and keep going. Okay, so that's the algorithm. And in termination, you want to show that you terminate the algorithm when the piece gets too small, meaning it's very, very unlikely compared to the parent, or you fix too many coordinates, which is a problem for us. Okay. And then you have to show that both of these events do not lose too much mass. They only lose exponentially small mass. Okay. Here's the outline again. We have the decomposition theorem, which we can show that these functions AUV are simple, from which we can show a lower bound on the non-negative rank of pattern matrices, from which we get the CSP lower bounds. Okay. So let me finish with some open problems. I think the main open problem going forward is showing a similar result for a semi-definite rank, for positive semi-definite rank. Here, the best lower bound is n to the omega log n, coming from the work of Lee, Raghu, and then Stoiter, but it's from completely different techniques. So there's nothing which is kind of bridging the two right now. And the second open problem, which also came up in Meka's talk, was to prove a lifting theorem for non-negative rank when the alphabet size is constant. Okay? So right now, we have a tight lifting theorem, but the alphabet size had to be some 10 times log n. But if you show it for a constant, all of the CSP lower bound, or many of the CSP lower bounds I mentioned, instead of being sub-exponential, for instance, will become exponential. To beat 7/8 plus epsilon, you need 2 to the omega n size LPs. It's kind of ETH for extended formulations. And finally, there are many other interesting gadgets for which we'd like to prove lifting theorems. For example, lifting theorems for permutations. So here, think of the rows being bit strings and the columns being permutations. And the x pith entry is f of pi of x. Can we characterize the non-negative rank of this lifted matrix in terms of some property of f? Okay. And in a very recent work, Lee, myself, and Vidic, and Pasin, Raghavendra, and Yuen found a simpler analysis of the theorems that I mentioned, the lifting theorem for non-negative rank, but that's for the indexing gadget. It's kind of an asymmetric gadget, but you can get the same results for CSPs as we did using a much simpler analysis. Okay. Thank you.
Are there any questions? Yeah.
I guess I have a few questions. So first, is the difference between what CLRS did and what you're doing is like you're using min-entropy, rather using entropy somehow when you're trying to decompose?
That is a difference, but I'd say that's a minor one.
It's a minor one.
It's probably a minor one.
So okay, and where did so I kind of got lost as to where the gadget fits into the lifting theorem.
Right. So this decomposition theorem is gadget oblivious, right? I mean, you're just showing something for distributions.
There's no gadgets there.
Then there's no gadgets there. Where gadgets show up is this example 3 that I here. G is a two-source extractor. Right. So here I said like if Uj and Vj, for example, are high entropy, you want the output of the gadget to be close to being uniform. Okay? And this is true only for certain kinds of gadgets.
Okay. But
The main difference is your definition of approximate junta. I mean, it's a non-trivial definition, which is.
Oh, you mean from CLRS? Yeah. To answer your first question, James is pointing out that one of the main differences is CLRS is trying to find junta approximations. And if you dig into what we are doing, we're finding approximations in a very different sort of error metric.
Okay.
I can tell you about that more. Yeah.
So, but regardless, your decomposition theorem has no gadget.
There's no gadget in it. Yeah.
You plug it.
Right. And in the simpler analysis that I mentioned, it's for another gadget, the indexing gadget, which is kind of the mother of all gadgets. If it's true for any gadget, it's true for the indexing gadget. And so there the decomposition theorem becomes much simpler, but this extractor statement that I mentioned becomes a little trickier than what it is for inner product. Okay. Any other question? Yeah?
So the log and lower bound that you need is all because you need the extractor to work?
Sort of. I mean, you get... So what happens is that if you have gadget size b, then the error becomes like 2 to the minus omega b. Okay? So imagine that you have 2 to the error minus omega b in each of the coordinates. Now you have n coordinates. I want something statistical distance. I need to kill off 2 to the minus b with n. Okay? It's not strictly true, but that's one of the things. And that's one reason why this analysis breaks down when you take b to be a small constant.
Other questions? All right, then let's thank the speaker again.